Hello, and welcome. In this video, we will introduce the fundamental concepts of vectors, which are essential for IB mathematics analysis and approaches higher level. By the end of this session, you will be able to distinguish between scalars and vectors, represent vectors geometrically, perform basic vector operations like addition, subtraction, and scalar multiplication, and extend these concepts to vectors in three-dimensional space. Let's begin with a classic problem. Imagine an aeroplane flying at 800 kilometers per hour due east. A cold wind suddenly blows from the southwest at 35 kilometers per hour. How does this wind affect the plane's movement? To solve this, we need to consider both the speed and the direction of the plane, and the wind. This leads us to the core idea of vectors. Our first objective is to understand the difference between scalars and vectors. A scalar is a quantity that has only magnitude, or size. It does not have a direction. Think of things like speed, mass, time, or temperature. For example, a speed of 800 kilometers per hour tells you how fast something is moving, but not where it's going. A vector, on the other hand, is a quantity that has both magnitude and direction. Velocity is a perfect example. The plane's velocity is 800 kilometers per hour due east. This tells us both its speed and its direction. Other common vector quantities include acceleration, displacement, and force. For instance, if a farmer pushes a fence post, the effect depends on how hard he pushes, which is the magnitude of the force, and the direction in which he pushes. Force is a vector. Now that we know what a vector is, how do we represent it? Our next objective is to represent vectors geometrically. We can represent a vector using a directed line segment or an arrow. The length of the arrow represents the magnitude of the vector, and the arrowhead shows its direction. Let's look at an example. Suppose we want to represent a force of 30 newtons in a northeasterly direction. First, we need a scale. Let's say 1 centimeter represents 10 newtons. So a 30 newton force will be represented by an arrow 3 centimeters long. We draw a compass rose to establish our directions. Northeast is exactly halfway between north and east, so it's at a 45-degree angle from the east axis. We draw an arrow 3 centimeters long in that direction and label it 30 newtons. This arrow visually captures both the magnitude, 30 newtons, and the direction northeast of the force. We have now met our objective of representing vectors geometrically. Next, we'll learn about vector notation and some fundamental vector properties. Our objective is to understand how to write vectors and what it means for vectors to be equal or negative. A vector from point A to point B is written as AB with an arrow above it. The magnitude, or length, of this vector is written as the absolute value of AB. A special case is the position vector, which starts at the origin O and ends at a point A. This is written as OA, or simply as a lowercase bold letter, like A. The magnitude is written as the absolute value of A. Two vectors are considered equal if they have the exact same magnitude and the exact same direction. This means they are parallel, point the same way, and have the same length. We can draw an equal vector starting from any point, which is why we say vectors are free. The negative of a vector A is a vector with the same magnitude as A, but pointing in the opposite direction. It is denoted as negative A. For example, the vector from B to A, BA, is the negative of the vector from A to B, AB. Let's apply this to a parallelogram. Consider parallelogram PQRS, where vector PQ is A and vector QR is B. First, let's find the vector QP. Since QP is the vector from Q to P, it's the negative of PQ. So QP equals negative A. Next, let's find senior. In a parallelogram, opposite sides are parallel and equal in length. Therefore, vector SR is equal to vector PQ. So SR equals A. Finally, let's find SP. SP is the vector from S to P. It is parallel to QR and has the same length, but it points in the opposite direction. So SP equals negative B. We have now successfully used vector notation and properties to describe vectors within a geometric figure. Our next objective is to perform geometric vector addition. This is a crucial operation that allows us to combine vectors. The principle of vector addition is often called the triangle rule. If you have two vectors, a and b, to find their sum, you place the tail of the second vector, b, at the head of the first vector, a. The resultant vector, a plus b, is the vector that goes from the tail of a to the head of b. Let's visualize this with an example. Suppose we have two vectors, a and b, on a grid. First, we draw vector a. Then, starting from the head of a, we draw vector b. The vector that connects the tail of a to the head of b is the sum, a plus b. This is the triangle rule in action. A key property of vector addition is that it is commutative. This means a plus b is equal to b plus a. We can show this using the parallelogram rule. If we draw a and b from the same point, their sum is the diagonal of the parallelogram they form. Whether we add a to b or b to a, we get the same diagonal. Another important concept is the zero vector. The zero vector, denoted by a bold 0, is a vector of length 0. It has no direction. When you add a vector to its negative, you get the zero vector. For any vector a plus the zero vector equals a. Let's practice simplifying vector expressions using these rules. Consider a pentagon a, b, c, d, e. What is the sum of vectors bc and ca? Using the triangle rule, the vector from b to c followed by the vector from c to a is equivalent to the single vector from b to a. So, bc plus ca equals ba. Now, let's try a longer chain, ab plus bc plus cd plus de. This is a series of displacements. The vector from a to b, then b to c, then c to d, then d to e, is the same as the single vector from the starting point a to the finishing point e. So, the sum is ae. What about ab plus bc plus ca? This path starts at a, goes to b, then to c, and finally back to a. Since the starting and ending points are the same, the total displacement is 0. The sum is the zero vector. We have now successfully performed geometric vector addition and simplified expressions using the triangle rule and the concept of the zero vector. Our next objective is to perform geometric vector subtraction. This operation is closely related to addition. To subtract one vector from another, we simply add its negative. So, a minus b is defined as a plus the negative of b. Let's see how this works geometrically. Suppose we want to construct a minus b. First, we draw vector a. Then, we draw the negative of vector b, which has the same length as b, but points in the opposite direction. We place the tail of negative b at the head of a. The resultant vector from the tail of a to the head of negative b is a minus b. Let's try a more complex example. Given vectors r, s, and t, let's construct s minus t minus r. First, we draw a vector s. Then, we draw the negative of t and place its tail at the head of s. Finally, we draw the negative of r and place its tail at the head of negative t. The resultant vector connects the tail of s to the head of negative r. This is s minus t minus r. We can also use this rule to simplify vector expressions algebraically. Consider points a, b, and c. Let's simplify a, b minus c, b. We can rewrite this as ab plus the negative of c, b. The negative of cb is b, c. So we have a, b plus b, c, which, by the triangle rule, simplifies to ac. Let's try another one. ac minus bc minus db. We rewrite this as ac plus cb plus bd. Following the path, we go from a to c, then c to b, then b to d. The resultant vector is AD. We have now successfully performed geometric vector subtraction and used it to simplify vector expressions. Our next objective is to understand and apply geometric scalar multiplication. This is how we change the magnitude of a vector. A scalar is just a number. When we multiply a vector by a scalar, we are performing scalar multiplication. The result is a new vector that is parallel to the original vector. If the scalar k is positive, The new vector k times a has the same direction as a, but its length is multiplied by k. For example, 2a is a vector twice as long as a in the same direction. If the scalar k is negative, the new vector k times a has the opposite direction to a, and its length is multiplied by the absolute value of k. For example, negative 3a is a vector 3 times as long as a, but pointing in the opposite direction. If the scalar is 0, the result is the 0 vector. This makes sense, as a vector of 0 length has no direction. Let's combine this with addition and subtraction. Given vectors r and s, let's construct 2r plus s. First, we construct the vector 2r, which is twice the length of r in the same direction. Then, we add s to it using the triangle rule. The resultant vector is 2r plus s. Now, let's construct r minus 3's. This is equivalent to r plus negative 3's. We draw r. Then, we draw negative 3's, which is 3 times the length of s but in the opposite direction. We add this to r. The resultant vector is r minus 3's. We have now successfully performed geometric scalar multiplication and combined it with vector addition and subtraction. While geometric representations are great for understanding, they can be imprecise. Our next objective is to represent vectors algebraically in a coordinate plane. In a two-dimensional Cartesian plane, we can represent any vector using its components. The position vector of a point P with coordinates x, y is written as a column vector x, y, or in unit vector form as xi plus yj. Here, I and j are special vectors called base unit vectors. I is the unit vector in the positive x direction, and j is the unit vector in the positive y direction. They are called unit vectors because their magnitude is 1. For example, the vector 2i plus 5j means we move 2 units in the x direction and 5 units in the y direction. This is the same as the column vector 2, 5. Algebraically, 2 vectors are equal if and only if their corresponding components are equal. For example, if vector A is a1, a2, and vector B is b1, b2, then A equals B if and only if a1 equals b1 and a2 equals b2. Let's use this to find the components of a vector between 2 points. Suppose we have points a, 1, 4, and b4, 5. The vector BA is the vector from B to A. To find its components, we subtract the coordinates of the starting point from the coordinates of the ending point. So BA is 1 minus 4, 4 minus 5, which gives us the vector minus 3, minus 1. We have now successfully represented vectors algebraically in the plane and found the components of a vector between 2 points. A key property of any vector is its magnitude. Our objective here is to calculate the magnitude of a vector in the plane. The magnitude of a vector is its length. If we have a vector A with components a1, a2, we can visualize it as the hypotenuse of a right-angled triangle. The horizontal side has length of 1, and the vertical side has length of 2. Using the Pythagorean theorem, the square of the hypotenuse is the sum of the squares of the other 2 sides. So the magnitude of A, written as the absolute value of A, is the square root of a 1 squared plus a 2 squared. Let's find the magnitude of the vector P equals 3 minus 5. The magnitude of P is the square root of 3 squared plus negative 5 squared. This gives us the square root of 9 plus 25, which is the square root of 34 units. A special type of vector is a unit vector. A unit vector is any vector that has a magnitude of exactly 1 unit. We've already seen the base unit, vectors I and j. Let's find the value of k such that the vector, minus 1/3, k, is a unit vector. Since it's a unit vector, its magnitude must be 1. So the square root of negative 1/3 squared plus k squared must equal 1. Squaring both sides, we get 1/9 plus k squared equals 1. Solving for k squared, we find k squared equals 8/9. Therefore, k is plus or minus the square root of 8 over 3. We have now successfully calculated the magnitude of a vector and identified unit vectors. Now we will perform algebraic operations with plane vectors. Our objective is to add, subtract, and multiply vectors by scalars using their components. Algebraic vector addition is straightforward. To add 2 vectors, you simply add their corresponding components. So if A is A1, A2, and B is B1, B2, then A plus B is A1 plus B1, A2 plus B2. Similarly, for subtraction, you subtract the corresponding components. A minus B is A1 minus B1, A2 minus B2. For scalar multiplication, you multiply each component of the vector by the scalar. So k times A is k times A1, k times A2. Let's work through an example. Given P equals 4, 1, and Q equals 2 minus 3, let's find P plus 2Q. First, we calculate 2Q by multiplying each component of Q by 2. This gives us 4 minus 6. Then, we add this to P by adding the components, 4 plus 4, 1 plus negative 6, which results in the vector 8 minus 5. Now, let's find the magnitude of a vector expression. If r equals 2i plus 3j and s equals negative I plus 4j, let's find the magnitude of r plus s. First, we find the vector r plus s by adding the components. This gives us 1, 7. Then, we find the magnitude of this resultant vector using the Pythagorean theorem. The magnitude is the square root of 1 squared plus 7 squared, which is the square root of 50. We have now successfully performed algebraic operations with plane vectors. Finally, we will extend these concepts to three-dimensional space. Our objective is to represent vectors in 3D and calculate their magnitudes. In 3D space, we use three mutually perpendicular axes, x, y, and z. The position vector of a point P, with coordinates x, y, z, is written as a column vector, x, y, z, or in unit vector form as xi plus yj plus zk. We now have a third base unit vector, k, which is the unit vector in the positive z direction. It has components 0, 0, 1. The formula for the magnitude of a vector extends naturally to 3 dimensions. The magnitude of a vector A with components A1, A2, A3 is the square root of a 1 squared plus A2 squared plus A3 squared. This is derived by applying the Pythagorean theorem twice. Let's find the magnitude of the vector C equals negative I plus 2j plus 3k. First, we write C in component form, which is minus 1, 2, 3. Then, we apply the magnitude formula. The magnitude is the square root of negative 1 squared plus 2 squared plus 3 squared. This simplifies to the square root of 1 plus 4 plus 9, which is the square root of 14 units. The rules for algebraic operations, addition, subtraction, and scalar multiplication, are exactly the same in 3 dimensions as they are in 2. You just perform the operation on the third component as well. For example, if A is minus 1, 3, 2, and B is 3, 0, minus 1, then A plus B is minus 1 plus 3, 3 plus 0, 2 plus negative 1, which gives us the vector 2, 3, 1. We have now successfully extended our understanding of vectors to 3-dimensional space. Let's return to our opening problem and solve it using the vector methods we've learned. The airplane is flying at 800 kilometers per hour due east. The wind is blowing from the southwest at 35 kilometers per hour. We need to find the plane's resultant velocity. First, let's express these velocities as vectors. We use a coordinate system where east is the positive x-axis and north is the positive y-axis. The plane's velocity is 800 kilometers per hour in the positive x direction, so its vector is 800, 0. The wind blows from the southwest. This means it blows towards the northeast. The angle from the positive x-axis is 45 degrees. The wind's velocity vector is 35 times the cosine of 45 degrees in the x direction and 35 times the sine of 45 degrees in the y direction. This gives us the vector 24.75, 24.75. The resultant velocity is the sum of the plane's velocity and the wind's velocity. Adding the components, we get 824.75, 24.75. The magnitude of this resultant vector is the square root of 824.75 squared plus 24.75 squared, which is approximately 825.1 kilometers per hour. The direction is the angle whose tangent is 24.75 divided by 824.75, which is about 1.7 degrees north of east. So the wind pushes the plane slightly off course to the northeast and increases its speed. This demonstrates the power of vectors in solving real-world problems. Let's recap what we've learned. We started by defining scalars as quantities with magnitude only, and vectors as quantities with both magnitude and direction. We learned to represent vectors geometrically as directed line segments, and algebraically using components in 2D and 3D space. We mastered the fundamental operations: geometric addition using the triangle rule, subtraction by adding the negative, and scalar multiplication to change magnitude and direction. Finally, we saw how to perform these operations algebraically by manipulating components and how to calculate the magnitude of any vector using the Pythagorean theorem. These concepts form the foundation for much of the vector work you will do in IB Mathematics AAHL. Now, let's test your understanding with some practice questions. Here are 5 practice questions designed to reflect the style of IB assessment. Pause the video, try to solve them on your own, and then resume to see the fully worked solutions. Question 1. Given vectors A equals 3 minus 2 and B equals minus 1, 4, find the vector 2A minus 3B. Question 2. The position vectors of points P and Q are P equals 2I minus J plus 3K and Q equals 4I plus 5J minus K. Find the vector PQ and its magnitude. Question 3. Find the value of the scalar K such that the vector K, 2K, 3, is a unit vector. Question 4. In a regular hexagon, A, B, C, D, E, F, let vector AB be U and vector BC be versus express the vector AD in terms of U and V. Question 5. Find the scalars A and B such that A times the vector 2 minus 1 plus B times the vector 3, 4 equals the vector 13, 2. Let's go through the solutions. Here is the solution to question 1. We are asked to find 2A minus 3B. First, we calculate 2A by multiplying each component of A by 2, which gives 6 and negative 4. Then, we calculate 3B by multiplying each component of B by 3, which gives negative 3 and 12. Finally, we subtract the components, 6 minus negative 3, negative 4 minus 12, which simplifies to the vector 9 and negative 16. Here's the solution to question 2. We need to find the vector PQ. The vector from P to Q is found by subtracting the position vector of P from the position vector of Q. So PQ equals Q minus P. Subtracting the components, we get 4 minus 2, 5 minus negative 1, negative 1 minus 3, which simplifies to the vector 2, 6 minus 4. Now we find the magnitude of PQ. The magnitude is the square root of 2 squared plus 6 squared plus negative 4 squared. This is the square root of 4 plus 36 plus 16, which is the square root of 56. Here is the solution to question 3. We are given that the vector k2, k3 is a unit vector. This means its magnitude must be 1. We set up the magnitude equation. The square root of k squared plus 2k squared plus 3 squared equals 1. Squaring both sides, we get k squared plus 4k squared plus 9 equals 1. This simplifies to 5k squared equals negative 8. Since k squared cannot be negative, there is no real value of k that satisfies this condition. This vector can never be a unit vector. Here is the solution to question 4. We need to express the vector A, D in terms of U and versus. We can find a path from A to D using the vectors we know. One such path is A to B, then B to C, then C to D. We know A, B is U, and B, C is versus. In a regular hexagon, the vector C, D, is equal to the vector B, A, which is the negative of A, B. So C, D is negative U. Substituting these into our equation, we get A, D equals U plus V plus negative U, which simplifies to just versus. Here is the solution to question 5. We have a vector equation. We can rewrite the left side by performing the scalar multiplication and then the vector addition. This gives us the vector 2a plus 3b, negative a plus 4b. Now we equate the components of the vectors on both sides of the equation. This gives us a system of two linear equations. 2a plus 3b equals 13, and negative a plus 4b equals 2. We can solve this system. Multiplying the second equation by 2 gives negative 2a plus 8b equals 4. Adding this to the first equation eliminates a, giving 11b equals 17, so b equals 17 over 11. Substituting this back into the second equation, we find a equals 46 over 11. That concludes our introduction to vectors. We have covered the essential concepts and operations required for the IB Mathematics AAHL curriculum. Remember, vectors are a powerful tool for describing quantities that have both magnitude and direction. Mastering their geometric and algebraic properties will be key to your success in this topic. Thank you for watching. Here is a summary of the key formulas and concepts we covered today. Keep these in mind as you continue your study of vectors. We define vectors as quantities with magnitude and direction, and scalars as quantities with magnitude only. We learned to represent vectors geometrically with arrows and algebraically with components. We covered the algebraic operations for 2D and 3D vectors, addition, subtraction, and scalar multiplication. And we learned how to calculate the magnitude of a vector using the Pythagorean theorem. These are the foundational tools you will use to solve more complex vector problems. Keep practicing, and you'll build confidence in this topic.